Today we are very pleased to have with us Professor William Booth from Yale University. Just a little bit of background. Dr. Booth got his bachelor's degree from our sister institution, Binghamton University, in physics and math. After that, he actually worked in the private industry for a couple of years as an analyst before deciding to go back to school, graduate school, and then he went to MIT, got a professional master's degree in geosystems before going into atmospheric sciences and worked with Kerry Emanuel at MIT. After he got his PhD, he worked as a postdoc at Harvard, mainly with Ximing Huang for a couple of years, and then he moved to Yale as an assistant professor. So during his short career so far, Dr. Booth actually has already had a lot of achievement. He's already won the AGU Houghton Award, which is awarded to the young scientists in atmospheric sciences, who shows who has done a lot of good work already. And then he actually also got the ONR Young Investigator Award as well as the NSF Korea Award. So to see, he'll be talking about monsoon depressions today. So let's welcome Dr. Booth.
And let me know if I'm too loud or not loud enough. I've been told there's a microphone here. So thanks for coming, everyone. I'm going to be presenting work that I've been doing in conjunction with my group at Yale. In particular, I'd like to acknowledge the contributions of John Hurley, Naftali Cohen, who have been postdocs at Yale, and Varun Murthy, who's a grad student still continuing to work on this topic. The topic is monsoon depressions. I'm going to begin by acknowledging the fact that many of you may have no idea what a monsoon depression is or have even heard of these, so I want to thank you for coming to a talk on a topic that you may not be familiar with or even understand why it's important. This is a I don't know if you've ever played around with this tool or seen it used before, Google's Ngrams tool, which tells you how frequently words occur as a function of time in the books that are indexed by Google. And there's quite a few books that are indexed by Google, believe it or not, full text. And it would be ideal from my point of view, to have this for scientific papers, but this is the closest I could come to that. And the point is that there's a number of phrases that I've put up here. Something like climate change, you can see there was very little discussion of it through the 1800s and 1900s until the mid to late 1980s, after which time the occurrence of the phrase climate change began to increase dramatically in English language books. Other climate phenomena like monsoon, typhoon have been fairly steady over time in the relative frequency with which they occur. Monsoon depressions, there's this peculiar time series which actually has a peak in the early 1980s and then drops off to a very low number again. And I did have to multiply this by 300 to even get it on the same scale as something like climate change. But my point is to acknowledge the fact that this is not a topic that has been widely studied. There was a brief flurry of activity on it in the late 1970s, early 1980s, and since then there hasn't really been very much work done at all. And so that's one of the reasons why I'm working on this is because I think that these are very important storms from a societal perspective, very interesting dynamically, and yet there isn't a lot of work going on to understand their fundamental physics, how they've changed in the past, how they might change in the future. So we're going to talk about those things. I'm going to begin by saying a few words about what monsoons are, and then what monsoon depressions are. These are two different things, different spatial scales. And then we'll get into more the work that I've been doing, that my group has been doing, looking at the observed distribution of these storms and the mechanisms that essentially make them tick. So beginning with a short primer on monsoons. When I talk about monsoons, I'm not talking just about the South Asian or Indian monsoon, which is arguably the most well-known and is the most intense, but is only one of a number of monsoon regions around the planet. I've drawn red boxes around those regions. We have the South Asian monsoon, the West African monsoon, South American, and this monsoonal region here over Southern Africa that also doesn't get a lot of attention, but has fairly classic monsoon dynamics, and the Australian monsoon. There's also the North American monsoon, which doesn't look like much when you look at, I should have mentioned earlier, these are maps of precipitation during the boreal and austral summer seasons. And you can see that the North American monsoon is really just rainfall that occurs sort of on the periphery of this intertropical convergence zone region right here. And the key point is that monsoons are this seasonal shift of precipitation from one side of the equator to the other in these tropical to subtropical continental regions. You can see the South Asian region during its local winter is quite dry, and then during summer becomes very wet. And so over these tropical to subtropical continent regions, most of the rain falls in the summer season or the monsoon season. And in the tropics, especially if you're concerned about continents where people live, a very large fraction of the rain falls in these monsoon circulations. Monsoon circulations are often thought of in a very idealized sense, traditionally. Just for conceptual simplicity, often it's nice to think of a circulation in a latitude height plane where you have a continent that's off the equator and warm air is rising in the summer hemisphere, and cold air is sinking in the winter hemisphere. And the rising air is cooling adiabatically until it reaches its dew point and water vapor condenses and falls out as precipitation. You have flow across the equator to close the mass circulation. And because we're on a rotating planet, these symbols here denote wind going into the board, or your trade winds, your easterly winds. And in the summer hemisphere, the trade winds are reversed to become your low-level monsoon westerlies. And you have easterly winds in the upper troposphere. Now, this is a very idealized picture that really hides a lot of complexity that you get in the zonal mean. This is a plot of the low-level horizontal wind as these vectors. This is the 850 millibar wind. And the shading is precipitation. You can see that the red is upwards of about 25 millimeters a day of precipitation over this India, East African region. This is the Tibetan Plateau. There are some topographic contours in black here on this plot. And although there's a lot of zonal asymmetry here, a lot of complexity, nevertheless, that two-dimensional view that I put up on the previous slide does describe this to a decently good degree. You have precipitation in your summer hemisphere. You have low-level monsoon westerlies. You have your trade winds, your easterlies in the southern hemisphere. And you have flow at low levels from the winter hemisphere into the summer hemisphere that in this region is highly concentrated in longitude into this Somali jet region here just off the east coast of Africa. And when you look at the temperature structure, when you look at the thermodynamics of this circulation, those circulations are in balance with this poleward temperature gradient. So the black contours are the upper tropospheric, the upper level temperature, and the red shading, the color shading, is the low level moist static energy, or roughly the energy content of the near surface air, that's coupled by moist convection with the upper tropospheric temperature. And my point in putting this up is to really, one, show the degree to which the South Asian monsoon dominates the global picture. The South Asian monsoon really is the global temperature maximum of the troposphere during boreal summer. And to emphasize that we're going to be looking at smaller scale storms that are embedded in this large scale picture. in other words, we're going to be looking at storms in this region right here, predominantly. And that's the region where the temperature increases as you go toward the pole, instead of increasing as you go toward the equator. So in monsoon regions, the temperature gradient is reversed in direction. Temperatures increase as you go poleward. And so these storms that I'm talking about that are embedded in that large-scale monsoon regime are about 2,000 kilometers in their outer diameter. So big things in some sense, but they're substantially smaller scale than the circulations we were just talking about. This is here, the sort of black dotted line is the northeast coast of India. Here would be Bangladesh, and this is the Bay of Bengal. So we've zoomed in quite a lot. And this is a snapshot, essentially, of one monsoon depression that occurred in September of 2008. The vectors, again, show the low-level wind. You can see this cyclonic flow. And the color shading shows precipitation. About 45 centimeters of rain fell in one day, as estimated by the TRMM satellite, over this coastal region of the northern Bay of Bengal. And these monsoon depressions typically propagate. They most often form over the northern Bay of Bengal and then propagate to the northwest over India, where they produce a large fraction of the precipitation that falls over that continental region. These are very different in some sense, from tropical cyclones in that they can not only transit over a land surface, but they can even form over land surfaces sometimes. So they don't decay nearly exponentially as soon as they make landfall, like a typical hurricane or typhoon would. They're observed in a lot of ocean regions. In the northern and the southern Indian Ocean, there are Australian monsoon depressions also. These are not just a phenomena that's limited to India. And there are also storms called monsoon depressions in the western Pacific that are frequently associated with tropical cyclogenesis. You can get tens of tropical cyclones, typhoons a year that evolve out of these monsoon depressions. And they also create very intense floods. These are sort of my couple social impact slides to give you the extent of the devastation that can occur from flooding associated with monsoon depression type storms. Last year in June, there were these floods in this northern region of India near the foothills of the Himalayas called Uttarakhand that were related to a depression that came up from the Bay of Bengal and interacted with the topography and possibly a mid-latitude disturbance too, killed thousands of people. In 2010, there was floods in India and Pakistan. This shows the Pakistan floods, which ended up submerging about 20% of the surface area of the country of Pakistan. So you can see that in this river here, this is a year before the flood, the normal state of the Indus River in August, and then this is a few days after the flood. You can see just how much it widened. This is 25 kilometers. So you're talking about the river widening from a typical kilometer scale to something that's 10 to, in some places, near 20 kilometers width. Again, deaths in the thousands. These storms, despite their social importance, are not very well documented even. One of the data sets that we have to work with is the global data set of tropical cyclones. It's the so-called best track data set that's maintained by a number of different international agencies. This is the tracks from the best track data set from 1 year, summer of 1999, with typhoon intensity storms in green and storms below typhoon intensity in red. And then on the bottom, I've plotted low pressure systems, cyclonic vortices, some of which, about half of which, are typically monsoon depressions, from a database maintained by the Indian Meteorological Department, which does maintain one of these few track data sets of monsoon depressions. And you can see that in the best track archive, there's only one storm in that region, whereas the Indian Meteorological Department has around 10 or so. So these storms are not, you can't just assume that all of these things are in these sort of tropical cyclone best track data sets. A lot of them are missing from there. And so we don't even really have a reliable number, a reliable climatology of what, on a global scale, what do the tracks of these sort of monsoon depression type vortices and monsoons, where are they occurring? How many are occurring per year? What direction do they move? What speed do they move at? Things like that. We don't even really know that very reliably. Outside of this small region of the Bay of Bengal in India. And so those are the questions that I'm asking, is what is the global distribution of monsoon depressions, and what are the mechanisms that are responsible for their workings? And I separate those into two topics. Is what is the mechanism by which they amplify from some initial very small scale disturbance, and what is the mechanism that makes them move? So what are the mechanisms of growth and propagation? And to do that, we've used reanalysis data, the ECMWF Center, the ERA interim reanalysis, and we've objectively tracked cyclonic vortices in monsoon regions, and used that data set, that track data set, to examine the composite structure and dynamics of these storms. So I'm sparing you from a lot of the details of that tracking exercise, and just showing you some of the end results, which is this is a distribution that's actually fairly well known, because it just replicates what has been done for the Indian region. And that's by intent. I want to show you something that really compares well with this Indian track data set for that particular region, because it establishes that what we're getting in the reanalysis products is reliable. And this map shows in the red shading essentially the genesis distribution for Indian monsoon depressions. It shows the regions where they tend to form. And the shading is a number per square degree per summer season. You can see they form most often over the Bay of Bengal. You do get some formation, though, over the Arabian Sea and over continental regions. And then the vectors are the propagation velocities, the typical propagation velocities. So they form in this region, and then they tend to propagate toward the northwest over India, with some variation in their direction of propagation. But the canonical finding from previous field campaigns, previous studies of this Indian Meteorological Department data, is that they form over the Bay of Bengal, propagate toward the west-northwest, where they dump a lot of rainfall over India. Yeah.
So how do you define this? So you can track them.
Yeah.
So you have the definition.
Right. So what we've done is we've tracked 850 millibar vorticity maxima using an automated algorithm, and then we've stratified them by intensity in using definitions consistent with traditional ones for monsoon depression. So a monsoon depression needs to have a surface pressure minimum with relative to its surroundings of 4 to 8 hectopascals, and it needs to have surface wind speeds that are at least 8.5 meters per second, and up to about 13.5 meters a second. And once you get beyond about 14 meters a second, we put them in this other category called deep depressions, which is again a traditional definition. And we separate those out because we don't want to be looking at things that are sort of traditional tropical cyclones. So once you get into that tropical cyclone intensity, we sort of put those in a separate category. And so that was a very good question timing-wise for me, because it allows me to explain this is our stratification by categories, intensity categories, where we have the lowest intensity synoptic scale vortices in monsoon regions, the medium ones, which we're calling depressions, consistent with traditional definitions, and then these stronger ones, which have some overlap with tropical cyclones. And I zoom in here, and that was my only animation, so if you were expecting movies, that was as good as it gets. And again, the shading is the genesis distribution, and the tracks for the genesis distribution over this 34-year period. So you can see that the Bay of Bengal here is one very prominent region of monsoon depression genesis. You also have a lot of synoptic scale vortices with depression intensity occurring over Africa, many of which are probably African easterly waves. And then you also have sort of easterly waves in the eastern Pacific, and what are often called monsoon depressions in the West Pacific. And then we also show tracks for just 1 year for clarity. So you can see that there does tend to be a westward propagation in a lot of these regions, west or northwest. And having this sort of track data set, we can quantify how much rainfall these storms produce. And this is a map of the fraction of the summer precipitation that's associated with these disturbances. It's the fraction of the total summer rain that falls within 1,000 kilometers of the vortex center. So this is a fairly generous definition. This does decrease if you use a more conservative radius, down to about around 50%. The darkest blue colors are when you're around 80% of the total summer precipitation. The black contours show the climatological mean precipitation. And so you can see if we look over Africa here, you have your climatological mean precipitation maximum. And then you have this region north of that precipitation maximum, which would be over the Sahel region, where these disturbances produce the majority, in some places near 80% of the total rainfall. And that's a pattern that seems to hold in other regions, that when you go just a little bit poleward of the peak climatological mean precipitation, these storms produce a very large fraction of that precipitation. And incidentally, a lot of that region poleward of the peak ITCZ is the continental monsoon region. What I'm going to do now is examine in detail the structure of Indian monsoon depressions to look in a little more detail on how these work, using the Indian region as one of the prime examples. These are actually vortices that have a cold core in the lower troposphere. So this is a latitude versus height plot of temperature in colors and zonal wind in contours. So you can see cyclonic flow here, dashed being negative around the vortex center, which has a cold core at low levels. That sort of cold core structure in the lower troposphere is seen in these other regions. So if we look in the southwest Indian Ocean, in northern Australia, we see a similar sort of deep structure with a cold core at low levels. Doesn't occur everywhere. These disturbances that occurred over West Africa, the ones that I said might be more easterly wave, African easterly wave type disturbances, do have a very different structure. They're a lot more shallow. The circulation is trapped almost entirely below 500 millibars, and they're consist of a warm core that's down near the surface, centered around 850 millibars. That's over West Africa and also over this sort of interior region of Australia, which is also a very dry desert region. The deep disturbances, though, the Indian monsoon depressions, the ones that are precipitating, one thing that is interesting is they have a very deep potential vorticity structure. And so PV is a nice variable to look at because it's a conserved quantity in adiabatic flow. And you can invert the PV to obtain the full distribution of temperatures, winds, geopotential heights, etc. And unlike the vorticity in these disturbances, which you can see from the flow, this is now a longitude versus height composite of an Indian monsoon depression. I'm plotting here the meridional wind. And the vorticity in these disturbances, so the absolute or relative vorticity, actually peaks in the lower troposphere. But the color shading is the potential vorticity, which has a peak more near 500 millibars and sort of a top-heavy column that extends into the upper troposphere. That structure is also common, that deep PV column. You also see in these other regions, in the southern Indian Ocean, in the western parts, as well as in northern Australia. And in those shallow, dry disturbances that occurred over Africa and interior Australia, the PV structure is very shallow. It's sort of trapped near the surface in the lowest 100 millibars or so of the atmosphere. So these dry disturbances are very different in many respects, even though they have the same low-level vorticity intensity as these deep precipitating disturbances. So that gives you a little bit of an idea about how these things look like, what their dynamical structures look like, where they occur on the planet, roughly maybe how many occur each year. I'm now going to talk a little bit about the mechanisms that are responsible for their dynamics, and breaking that into two categories, the growth and propagation mechanisms. You can see from this list of references here that most of the theories for growth and propagation were, as I mentioned earlier, sort of in the late 70s, early to mid 1980s. And as far as theory goes, there hasn't been a lot done since then. There has been a little bit of sort of validation of that theory by a couple people working at in Iowa. The previous theories are that just like mid-latitude baroclinic waves, these disturbances exist in a region where there's a strong meridional temperature gradient. So it's pointing in the other direction, but you still have here, instead of having an equatorward temperature gradient, you have a poleward temperature gradient. But that temperature gradient still gives you baroclinicity, it still gives you potential energy that you can extract to put into the kinetic energy of these vortices. And that's at least been the theory that was advanced in the late 70s to early 80s. And the idea for the propagation is that it was controlled by low-level dynamics. And I'm just going to leave it at that for now, and we'll come back to that and be a little more detailed about what that means. I'm going to talk first about the baroclinic growth mechanism. And to give you a sense of the strength of the baroclinicity, I'm going to be comparing the zonal wind, the mean zonal wind, the climatological mean zonal wind of the background states, of the mean states, that these disturbances are embedded in. And the black line is for Indian monsoon depressions. So you can see that the zonal wind is eastward at low levels and westward at upper levels. So you have this easterly vertical shear associated with the poleward temperature gradient in this monsoon region. And it's pretty strong. We're talking about 15 to 20 meters per second difference in wind speed between the lower troposphere and the upper troposphere. I've also plotted the mean state zonal winds for hurricanes as the blue line, and for a particular type of baroclinic waves in which moisture is thought to play an important role. And these have been called diabatic Rossby waves. You can think of these as baroclinic mid-latitude storms that have been heavily modified by precipitation, by the diabatic effects of precipitation. And one of the points of this plot is, to emphasize obviously the change in direction of the wind shear, but to show that the baroclinicity of the mean states of these diabatic Rossby waves isn't that different from the baroclinicity of the monsoon depression mean state. However, when we look at several indicators of sort of traditional dry baroclinic growth, it seems fairly obvious that it's not that that's responsible for their growth. To have dry baroclinic instability, you need to satisfy sort of some necessary criteria for instability, like the Charney-Stern criterion, which says that the potential vorticity gradient of the basic state needs to change signs somewhere within the domain. And I'm plotting here the potential vorticity on a particular theta surface, a particular potential temperature surface. And you can see that it increases as you go poleward, and there's no obvious change in sign of the gradient. It just is generally a poleward gradient in this region. The temperature gradient at low levels, or the surface temperature gradient, is also poleward. So if you think of your surface temperature gradient being equivalent to a PV gradient, that doesn't give you a change in the PV gradient sign either. Even more telling, though, is the fact that when you look at the composite mean potential vorticity of an Indian monsoon depression, you see this structure right here. Earlier I showed these in those sort of washed out purple colors. Here there's just this sort of rainbow color map. And you can see that these are a top-heavy 500 millibar maximum PV anomalies relative to the background state. And these are actually local maxima on isentropic surfaces, which are represented here as these black contours. And in dry baroclinic growth, all you get is adiabatic rearrangement of potential vorticity on isentropic surfaces. And you can't generate these local PV maxima. And you can actually see this when you look at case studies. If you look at the reanalysis data on isentropic surfaces, you see these PV anomalies sort of appearing out of nowhere. This isn't just a artifact of a compositing mechanism. We've sort of searched to see if you can get these intrusions of stratospheric air down an isotropic surface then get cut off or something, and we can't find any evidence for that. Another piece of evidence is that even when you consider how diabatic processes modify potential vorticity in baroclinic growth, the theories for moist baroclinic growth still require that you have to have this sort of upshear tilt of the PV structure. And you see that upshear tilt in this diabatic Rossby wave structure. This is a composite, a longitude versus height composite of the potential vorticity in a diabatic Rossby wave. And you can see that you have this high PV up near the tropopause as well as down near the surface. And the black vectors are the horizontal wind, the zonal wind at these two levels. So you can see that you have strong upper level westerlies, weak low-level easterlies, and so this column is tilting up shear. If the shear was allowed to tilt this, it would tilt it in that direction, right? But this is tilted against the shear. In the monsoon regions, the composite PV structure, again using a different color scale, because these PV structures are substantially weaker than the upper-level PV anomalies in these more extratropical Rossby wave disturbances. But you see that, if anything, the tilt is quite weak, and it's a little bit down shear in these Indian monsoon depressions. So there's not the upshear tilt that you need to even have it be baroclinic instability in a moist sense. That sort of says something about what these are not, that these don't, there doesn't seem to be evidence for sort of baroclinic growth in these disturbances. But, well, what does that leave? What is the answer? And we don't really have that answer yet. That's something that Varun Murthy, the grad student who I mentioned at the beginning, is continuing to work on. But we have a suggestion, and that is the fact that these are exhibiting these are behaving like the early stages, the very early stages of tropical cyclogenesis. When you look statistically at the associations, essentially the regression coefficients, between these climatological mean variables like relative humidity, low-level vorticity, convective available potential energy, and vertical wind shear, when you do that for tropical cyclones, which are the gray lines, and these are the regression coefficients for tropical cyclone genesis as it's statistically associated with these different environmental variables, you can see that tropical cyclones and these monsoon depressions have very similar statistics. So they're behaving statistically relative to climatological mean variables very much like tropical cyclones. So I'm going to set aside now the somewhat incomplete story for growth. We've said a little bit about what it's not, and essentially that this existing idea that these are drawing energy from the mean meridional temperature gradient, or the potential energy associated with that, doesn't really seem to hold water, and made a suggestion about that they're maybe behaving a little bit like the early stages of tropical cyclogenesis. Now I'm going to move on to the mechanism of propagation. And the early puzzle behind these storms was that they were thought to be, well, they are vortices that are concentrated at low levels in a region where the mean wind is to the east. And even though the mean wind is to the east, they're moving in the other direction, to the west. And you can see that here, that this is a composite of the relative vorticity in colors and the climatological mean zonal wind in the black line. So the thick black line is the zero wind line. Here we have our upper level easterlies, our low level monsoon westerlies. We have this bottom heavy vorticity column that's embedded in, that most of which exists in this region of eastward flow, and yet these move to the west northwest. So they're moving upstream of the mean flow in which they're embedded. And the old idea that goes back to, I think, 1971, in a paper by some people from India was that if you put a vortex in a vertically sheared flow, or equivalently, if you put a vortex in a temperature gradient, these are my schematics for the monsoon temperature gradient, colder near the equator, warmer as you go toward the pole in that monsoon region. Here's your vortex. That you have, if you put a vortex in that temperature gradient, in that vertically sheared state, it'll be tilted. The wind shear is westward of height, so it'll be tilted by the wind shear. But then the wind shear also excites the interaction between the vortex circulation and the mean shear. It excites ascent down shear of the vortex and descent on the up shear side. So you get ascent west of the vortex center and descent to the east. And when you have ascent on the down shear side, you can't have flow through your surface. You have a zero vertical velocity at the surface boundary condition. So that means that you have to have ascent increasing with height, and therefore vortex stretching down shear of the vortex center. And that provides a positive vorticity tendency that it's been argued would then tend to shift this vortex in the down shear direction, or to the west, or against the mean flow. So that was the old idea. We looked at the low-level vorticity budget to see if that actually held up, and it turns out that it doesn't. This is the vortex center. These are maps, longitude-latitude maps of the composite mean terms in the vorticity budget at low levels. And this is the observed vorticity tendency. Red is positive tendency and blue is negative. And so if you have a vortex that's centered on the black dot, and you have a positive tendency to the northwest and a negative to the southeast, it's going to move to the northwest. So this is just the tendency that you need to get the northwest propagation. So this is what's observed, essentially. And when we look at the low-level vortex stretching, you notice that it's actually rotated so that it would produce propagation to the southwest, not to the northwest. So one, it's the peak ascent is to the southwest of the vortex center. It would give you propagation in the wrong direction. And if you look at the magnitude of the tendency, you can actually see this color bar is about 3 times as strong as the observed tendency. And so what happens in reality is that a lot of the vortex stretching is offset by horizontal vorticity advection. And that's actually a common thing that happens in this sort of dynamics, this offset between the vortex stretching and the advection, is more well known, I think, in the tropical cyclone community. It suggests that when you put say a tropical cyclone in wind shear, it doesn't immediately get sheared over. It doesn't immediately get tilted by the shear. Instead, the shear excites these vertical circulations and vorticity tendencies that work to keep the vortex upright. And so that's what's happening here, is that the shear is trying to tilt these things over, and these stretching terms are basically just keeping the vortex upright. It's a concept known as sort of vortex resiliency, that the circulation sort of works against the shear to keep it from just being tilted over. I introduced potential vorticity earlier because I think it gives us something that turns out to be very useful for thinking about the propagation of these disturbances. The top plot shows the same climatological mean zonal wind that I plotted earlier, but now it shows the composite mean potential vorticity of monsoon depressions. And you can see that they're not as bottom-heavy as you might think by looking at the relative vorticity. They actually have a PV maximum that peaks just above the zero wind line. And so it makes you wonder, oh, well, maybe because potential vorticity is conserved, these are just being advected along with these slow upper-level easterlies just above the 500 millibar level in this mean monsoon flow. However, when you look at the total zonal wind, again, is latitude and height. The PV fields are the same in these two plots, but now we're showing the total composite wind instead of the time mean climatological flow. You can see that these are very strong disturbances. The total flow is strong compared to the time mean. And in other words, the advection might be nonlinear rather than just linear advection by the mean flow. And you can see that is actually what happens. And we get a picture that turns out to have a little bit more in common with the mechanism by which tropical cyclones propagate. And let's look first at this plot on the right, which is again a plan view of the vorticity in colors, just to show you where the vortex center is. And then I've plotted these vectors, which are the mean wind, which is a small green vector. So you can see the mean wind is quite weak at this 500 millibar level that I'm illustrating here. And the vortex propagation velocity is this red vector. So the mean wind is way too weak to explain this vortex propagation at about 2 meters a second or so to the northwest. But the total wind actually has a very comparable magnitude. It's a little bit too far northward, but it's much more like the total vortex propagation than the mean wind. And so that's some evidence that you really need the total wind, that this is sort of propagation by nonlinear advection. And the contours here are the azimuthally asymmetric component of the horizontal stream function. And dashed contours are flow like this. They are a cyclonic flow, and solid contours are anticyclonic flow. And this sort of structure to the component of the stream function that's azimuthally asymmetric about the vortex center is very similar to what you see in idealized solutions for beta drift of a tropical cyclone, where you put a vortex on a rotating sphere, it perturbs the background vorticity field to create these beta gyres. I thought I had that on here. Yes. These beta gyres, southwest and northeast of the vortex center, that then advect the vortex by producing net flow across the vortex center to the northwest. And so we're really suggesting that rather than propagating by this sort of interaction of the low-level dynamics with vortex stretching, that these things are just propagating by adiabatic beta drift. And it's not obvious, I think one thing that's interesting is it's not obvious that potential vorticity would even work very well for these disturbances because they're heavily precipitating, and potential vorticity is only conserved for adiabatic flow. But the PV tendencies due to propagation are actually much stronger than the diabatic tendencies associated with the growth and the precipitation. And so it is in some ways a little bit fortuitous that that adiabatic PV advection ends up working so well to explain the propagation. Another way of looking at it is that the propagation is fast enough, the adiabatic advection is fast enough that it sort of dominates over any diabatic effects in terms of the propagation. Okay, now going to a sort of different topic altogether, which is how have these storms been changing over time? This is something that you may not have heard about if you haven't heard about monsoon depressions, and I'm guessing that many of you have not heard about monsoon depressions prior to today. But a big story for people who study the Indian monsoon is that over the past century or so, if you use the records that are kept by the Indian Meteorological Department in that small region over the Bay of Bengal, Arabian Sea, and India, that the numbers of these monsoon depressions has decreased fairly dramatically. So they have records going back to the late 1800s, and the black line is just the yearly summer storm count, and the red line is just I think a 9-year running mean. And you can see that there is some variation, but the big story here is that there's been a decrease to, on average, about 2 or so per year from 6 to 7 per year in the earlier part of the 20th century. And these years in particular, 2002, 2010, and 2012, were noted for being the first summers in over a century of record keeping by the Indian Meteorological Department in which there wasn't a single monsoon depression that formed in the Indian monsoon. So that seems like a big deal, right? First summers in over a century that there was none of these storms formed. Now, when we did this automated vortex tracking in the reanalysis data, we actually found that, well, strangely, we actually got storms. We got monsoon depressions in 2002, 2010, and 2012, the years when they said that there were none. And this is a plot of the low-level surface wind in vectors and the surface pressure, showing you when you look in detail, when you just look by eye at the reanalysis maps of pressure and wind, and you look at the tracks that our automated algorithm gives, it seems to hold up. The algorithms don't seem to be doing anything crazy. And you can look at scatterometer data over ocean, some of which can actually give you vector wind direction as well as speeds, which are shown here in the colors. And you can look at precipitation from satellite, from the TRMM satellite, which is the 40 millimeter a day contour is shown in the magenta right here. And the scatterometer data validates the fact that the winds have this cyclonic flow structure, circular in this region. The wind speeds are easily surpassing the 8.5 meter per second surface winds you need to get classified as a monsoon depression, and they're heavily precipitating. And so it seems that simply the Indian Meteorological Department's record is missing some storms in these years. What we've also done, just sort of giving you the very short, high-level version of this story, is that we've tried to search for trends in a number of other data sets. These are the trends using a number of different regression techniques that are estimated over two different periods. One is the last about 34 years or so, and then these are other trends that were estimated just since 1989, a slightly shorter period. These top two plots are the two, this is the Indian Meteorological Department trend, so you can see it's negative, and this is the gray bar is the trend, and the error bar here is the uncertainty, the 95% confidence interval for the trend. This is another sort of by hand manual analysis that was done by an investigator named Sika, as well as earlier colleagues of his. And they found an even stronger trend done based only on surface pressure maps that were also put out by the IMD. Now, it can be dangerous to infer storm trends, storm count trends from reanalysis products, because we're talking about reanalysis products that are in more recent times assimilating satellite data. In the earlier part of the record, they weren't assimilating satellite data, so maybe you were missing some storms, although it's not obvious that you'd be biased low. Perhaps the models are too cyclogenetic, so maybe you'd be biased high in the absence of observations. But nevertheless, we took our estimate of monsoon depression tracks and fit a trend line to it. We got no statistically significant trend. There's a group at NYU's campus in Abu Dhabi that has very recently, in work that is only now in review, been doing a similar exercise for just Indian monsoon depressions, where they've been tracking them in several different reanalysis products. We took their data, and we similarly couldn't find any trends. And then we looked at satellite-derived surface wind speeds from scatterometers, and we counted the number of times that the kinetic energy of the surface wind over the Bay of Bengal exceeded a threshold, played around with several different thresholds. We looked at the summer average surface wind kinetic energy, and in those scatterometer data, we couldn't get a statistically significant trend either. So there's no real clear answer here as to, okay, we haven't proven definitively that there's no trend, but my point is that there is this very important question of, are these storms changing over time? And I think we've demonstrated there are some issues with the one long-term data set that we have on which this plot is based. And using some other data sets, although there might be issues in terms of the length of the data or the underlying data that they're assimilating, we haven't been able to find a trend anywhere else yet. So I'm going to close with that and just really summarize by saying that monsoon depressions are storms that have, in recent decades, been rather little studied. They're poorly understood. There's been a number of previous theories that go back 20 or 30 years, which we've been examining with modern data, larger numbers, of storms, looking at composite means, et cetera. And what we see seems to be inconsistent with those previous ideas of baroclinic growth and propagation by what's called quasi-geostrophic lifting, by the interaction with the vertical wind shear. Instead, monsoon depressions seem to be potential vorticity maxima, or that seems to be an efficient way to describe them, in the mid-troposphere rather than bottom-heavy vorticity columns. They are that, but we're arguing that it's more useful to describe them as mid-tropospheric PV maxima that propagate primarily by beta drift, by this nonlinear self-advection, and that somehow have moist convection intimately associated with their amplification. And I think that there's really a need for more study of these storms, more than can be done just by my group alone, in terms of their dynamics. And also, I think the end of my talk, I convinced you that there's a need for more observational analyses, more estimates of long-term trends, more assessments of how these things are changing in climate models in the future, whether climate models, whether numerical weather prediction models are doing a good job of forecasting these, of simulating these. And so I'm hoping that this work will, to some degree, prompt at least a few other people to work on these topics. So I'll close there, and I'm happy to take questions.
Thank you. So, questions?
Is there some modeling component to this? I think it's a perfect program for some idealized model.
Yeah. We are working on that. We don't have finished results yet. We've done a number of things. We've actually tried to use the WRF model in a sort of idealized beta plane simulation with just an aquaplanet SST. You get disturbances. They don't have a potential vorticity structure that looks like the observations. So we've sort of changed tacks a little bit to do more initial condition cloud resolving model simulations, and those are ongoing now. So yeah, stay tuned.
Yeah, very interesting. When I look at a figure like this, for example, and so forth, I wonder the analogy with these mesoscale convective vortices.
Yeah. Yeah.
So you didn't mention that, but they did show up in your climatology. Those living in the continents, like over the central U.S. and grow up scale and so forth, and they're highly nocturnal, but they do fall along baroclinic zones, and there have been studies highlighting that. So yeah, I was curious about that, and then I'm still wondering where this mid-level PV is coming from, at least the hypothesis of this PV, because I'm thinking of, if there is a latent heating contribution, right? So
I think there has to be. I mean, I think that there has to be a latent heating contribution. I would argue that you're getting that mid-level PV just because you have deep convection, and
So is the heating above there? Because I'm trying to think of where the PV is being generated, because to get a PV like that, you need the PV to be above.
You need the peak heating to be, at 400 millibars or something like that.
I guess that's it's like the trailing stratiform analogy, but it just seems higher than what many studies have documented for MCS.
Right.
Like
Yeah. Well, and that I don't know if I still have that slide here. Yeah. So this is my sort of schematic comparison. When you look at I may not be talking exactly about your MCS literature, but there's a paper I think by might have been Raymond and Zhang where they talk about the PV in a mesoscale convective system and how these things can sort of stay upright against the shear, and and that literature sort of leads into this diabatic Rossby vortex literature. So I kind of, this might not be correct, but I kind of think of those as being very closely related, the mesoscale convective system and sort of the diabatic Rossby vortex literature. So if that's true, when you look at these composites of diabatic Rossby vortices, just like the composite structure I showed you earlier, they tend to have a PV anomaly that's concentrated near the surface. I think the diabatic heating does tend to be a lot more bottom heavy. And maybe it's just that the diabatic heating is a lot more top heavy in this sort of tropical region than in this sort of mid-latitude baroclinic region. I think those are worthwhile exploring. Yeah.
Yeah, actually, this is sort of follow up on this. So I was going to ask you about whether you have done energetics. So it seems that you've done that.
Yeah, this is not. I think this is more for like a case study. We did this. This is consistent with Krishnamurti at Florida State has also done this sort of Lorentz energy cycle for a couple monsoon depressions, and gets fairly similar numbers. That they're heavily, the energetics are heavily dominated by diabatic processes rather than baroclinic conversions. That doesn't mean that they're. I don't think that's. In terms of the diabatic Rossby vortices, these tend to have. This ratio tends to be about 3 for those, at least in the idealized models. So these would be even more diabatically coupled. I don't know if that means anything. But
the other point is that if it's diabatic, theory driven, then you would expect a negative PV anomaly somewhere. But it's not clear from your from your hypothesis that there is actually a negative PV. Because diabetic is only residual PV.
Right.
PV. So if you have a positive PV anomaly, you should have something to accompany a negative PV anomaly somewhere.
Yeah, although it doesn't necessarily need to be up top, right? I mean, it could be, in this idea of sort of PV being conserved on integrally conserved between isentropic surfaces. You could be sort of concentrating it in from this region, into this region.
Yes, it's down under the negative PV. How do you get? When you're heating, what you expect is that you are increasing the PV below the heating and increasing it above it.
Right.
So.
Well, but I mean, remember that just requires having a heating maximum that's about here or so. I think these are good questions. We haven't answered this obviously, but yeah.
If the PV is related to the latent heating, the monsoon precipitation is mainly concentrated at the west side of India and the east side of the Bay of Bengal.
Yeah.
So why is the vortex located at the Bay of Bengal, between the Bay of Bengal and India? So it's not consistent with the precipitation region.
Well, the peak precipitation in the South Asian monsoon tends to be, if you look at pretty high resolution, you have this band of heavy precipitation right here, and then sort of a periphery over this region, and then another orographic band here. So I think this is not too far from those regions. These aren't, like I mentioned about the fraction of total summer precipitation, these aren't producing most of the precipitation maximum. They're producing most of the precipitation a little bit away from the precip maximum. So here's a good. This is actually a numerical model result, but I think that most of the monsoon depressions are spinning up in this region, just outside this heavy red region, and then they're accounting for a large fraction of this precipitation here over continental India.
So over the Indian monsoon region, as you showed, there's some easterly jet in the upper level.
Yeah.
And in the Bay of Bengal, it's the axis region of jet. So, and then it will produce the Asia-tropic regional circulation. That's secondary circulation. And because of the jet axis region, could the meridional circulation related with the monsoon pressure region?
So you're saying there's a jet exit region over the Bay of Bengal?
Yeah, near the Bay of Bengal. If you compare the upper level solar wind, there's a jet exit region.
Oh, sort of down here. So you're asking whether there could be some. Oh, okay. I would say, wouldn't the exit be more over here? So this is the upper level temperature. So I was just sort of using this as like a stream function, right? So if there was a jet entrance region here, you're saying there might be some sort of transverse circulations that could produce lifting or. Yeah. Yeah. Maybe, perhaps. Yeah. It's an interesting idea. Yeah.
So I have a separate question regarding inconsistency in observation. So I'm sure you know that the coast of Bay of Bengal has many weather stations, and so it is, and also there is heavy ship traffic there, so it's very difficult to miss a large structure like this. And so there is, and then it is possible that the Indian Meteorological Department may have missed some event, say, in early 1900s. But
yeah.
it's very difficult to imagine.
Right. So yeah, I should clarify. I'm not arguing that they're missing the storms. If you go back to like for 2010 and 2012, the annual monsoon reports for these things that we classify as monsoon depressions, they say there was a well-marked low pressure system in this region. They just for some reason don't classify it as a monsoon depression. One thing I worry about their data set is that, you know, when you go back to the 1890s and the early 1900s, that data set is based on, those storm counts are based on surface pressure observations that were communicated by telegraph to some central location. People were drawing, you know, analyzing those into maps by hand. Now they're categorizing these storms based on satellite observations and numerical model analyses. They used to categorize them based on surface pressure, now they're doing so based on surface wind speeds. There's been dramatic changes over time in the observing network as well as in the methods of analysis and the methods of storm categorization. And my fear is that that's a data set that just was never intended by the people who created it to be used in sort of climate trend studies, but yet it's being used as such.
Sorry, okay. One comment first, the topography precipitation, a maximum probably compared to the climate policy, not the depression itself. The two maximum precipitation we see in climate policy.
Yes.
The below the climate policy, not the depression itself. So that's a comment, yes, it's here.
Yes, so you're saying that these two precipitation maxima are orographically related?
Right.
Yes.
They are time policy, not depression itself. That's my question is about your diagram. Near the end of your talk. Show the diagram. Go back that one.
Sure.
Okay. It shows the PV position on the wind shear. Just wondering whether you based on some of the
Yeah.
PV you see is located to the east side of the east convection. You see that? I'm wondering if you have some observation evidence to support this diagram.
So the peak precipitation tends to occur southwest of the vortex center.
Here you're actually the east to west side, right?
So here's the PV. This is meant to be the west side.
Right.
This would be west. This would be east.
Side.
Yeah. So I'm just showing the XZ plane. So if you look in the XZ plane, it's west of the vortex center. If you look at a plan view, you'd see it's a little bit southwest of the vortex. It's southwest of the vortex center. That was when I showed the composite low-level vorticity budget. You had the peak stretching southwest of the vortex center. That's because that's where your peak ascent is. And if you look at just something like trim precipitation, you get about a 50 millimeter per day maximum southwest of the vortex center.
Will this be consistent with your north-westward movement of the?
Well, no, I think that's my argument is that quasi-geostrophic lifting, if you look at the QG omega equation, it actually gives you a peak lifting southwest of the vortex center, exactly where you see the observed precipitation and the reanalyzed descent. But my argument is that the vortex stretching that you get from that QG-induced descent is really kind of incidental to the propagation. There's other canceling terms in the vorticity budget, like horizontal advection, and that's something that when you look at this concept of vortex resiliency, how vortices tend to maintain their upright structure in a sheared environment, that the shear is never that in that vortex resiliency framework, no one argues that these vertical circulations produce propagation. They just argue that it keeps the vortex upright. Yeah.
Okay, I think in the interest of time, we should stop here. Yeah, very interesting discussion, and all of you are welcome to join us for lunch in 1:15. So, thank you.
Thank you. Okay, great. Did you any comments? Did you buy the beta drift argument or? Oh. Yeah.
But I don't know about it's actually criteria. But the trend that you see if you look at it, it seems that if you calculate the trend from 1989 to now, it's probably very different.
Right. And
so your barometer one is based on that. But one might imagine that prior to that, with without the barometer, you have to see light or like at this time.
Right.
That could also trend before.
Yeah.
No.
Oh yeah. No, I mean that's what I'm trying to say is that essentially maybe there is a trend, but my argument is that unlike previous people have just assumed there is a trend and it's been proven. And my argument is that there may be a trend, but we have not clearly established that there is a trend.
Like
well, in a way, although I think with tropical cyclones there's a big difference because there's been teams of people poring over historical analyses of tropical cyclone activity for decades.
But they are really right.
Well, no, but that's my point. And even then, they're still revising them.
Yeah.
These monsoon depressions, no one's really looked at them, and so to sort of assume that when you put 10% of the amount of work in, or even less.
But in reality, that happens. So you imagine, not now, but you think about where the center of action, you're making a note of where that center of action is. So in some sense, there is a hybrid situation. You want to stop here. The question is intermixing the same location for constant. That's the fact. We look at two separate problems. There's a single thing with multiple.
One fact is to realize all this time with it.
People have been talking situation where New York City has a single thing and Boston, Western boundary mile. That's almost making a note of it eventually, and then they were thinking about having a single thing.
Forget about all that. I'm not going to worry about all that. But the question is really,
these are the complications.
people look at
But I'd like in your terms, breaking up the time. Otherwise, I'm afraid when you do these composites,
have you done that? So actually that would be should be quite interesting. Because I think I never saw a thing about
Okay,
that's why
John
did that. If you know the vertical shift, you can always calculate the temperature once the sun is somewhere to somewhere. So how they told me that, and you did that right? It's Celsius. Do you know how to talk about?
Which one?
I don't know what, I don't think he actually did a paper. I think he did.
Are you talking about the transport not changing?
No, not that paper, but sometimes he measures the temperature. Okay, forget about something because I know something about
So then,
but if you have hands on that, you can calculate vertical shear.
yeah, I did vertical shear.
So if you can calculate vertical shear, then you can calculate horizontal temperature reading.
Yeah.
Right? So if you start from far out with the temperature doesn't change much, you always come in. Okay? So basically you will know the temperature chart.
Yeah.
So if you know the temperature and the velocity, then you can calculate the distance.
Yeah. Yeah, I know, and I would say we have a pretty good idea what that's going to look like. If you're interested, if you're asking me because of the variability that everyone discusses and the changes they see, this is just honestly and we have 20 years of the oleander, and it's just, I mean, trying to track that action from that, of whether it's an upward or downward trend, even if we did see one, it's pretty negligible. I mean, internal variability is more likely.
No, I don't agree. I think it could be pretty interesting because yes, I know you only have 20 years, but that's the longest. And